Okay. Welcome, everybody, to our session today. I'm Kristen Dana, one of the program chairs. I'm going to introduce Kavita Bala, who is our keynote speaker for today, Tuesday session. Kavita is a full professor at Cornell University in the Computer Science Department. She did her undergraduate work at IIT Bombay and her MS and PhD at MIT. She is the editor-in-chief for ACM TOG, and she has numerous awards, NSF Career, Excellence in Teaching. She's a founder and chief scientist for a recent startup called GrockStyle. I got to hear about GrockStyle for the first time in 2016 at the LDV Summit in New York City, which had an entrepreneurial competition, which GrockStyle won. It really, the technology, what can I say, it blew me away. I think it will when you see it too. It revolutionizes retail, giving you a way to have friction-free shopping with just images. So without further delay, let me introduce Kavita.
Thanks for having me. Thank you for the generous introduction, and thank you for having me. I'm really enjoying learning about this conference, and I'm looking forward to seeing also all the other posters today too. So the title of the talk has changed. I apologize. You write the abstract at a certain time, and 1 month later you're like, but I want to talk about different stuff. So I'm going to talk about materials and style. The original title only said materials. And you'll see, in fact, we'll talk about a recent launch with GrockStyle that she just mentioned, and we'll go from there. All right, so first let's, what's the best way to do this, actually? Because the mic is here. Does that work? Can you guys still hear me? Yeah, something bad happened there when I tried to switch. Sorry, I should have done this earlier. And yeah, there we go. Okay. Ooh, that's not good. Almost. And we'll wait. Great. The world we live in is full of rich materials, and we kind of take them for granted a little bit, but our entire life depends on the beauty, the functionality, the aesthetics. All of this come together in the worlds we live in, and materials have not actually received the attention they deserve. So one of the sort of the clarion calls of this talk is that material recognition, material understanding requires more investment from the computer vision community. So I'll talk about that a little bit. But one of the things that's always motivated me is to understand how it is that humans recognize materials and what it is about what you see that immediately makes you understand what you're working with in that context, and can we convert that into computer vision and computer graphics algorithms so that the machine can do the same level of recognition. So that's sort of the high-level theme of the talk. And I'll show you an example here. And actually, can we kill the white lights here? Is that possible at all?
Then we won't see you on the camera.
That's okay. I want you to see the images. You know how I look. Not going to change over the talk, but the images are going to change. So you look at this, and on the left, you can immediately recognize, I assume, that you're seeing something, a silk fabric. And on the right, and if the light's particularly dim, it's very obvious that there's velvet. And in fact, I'm wearing a velvet shirt, and probably no matter where you're sitting, you can probably recognize that I'm wearing a purple velvet shirt. But what does make silk look like silk or velvet look like velvet? I'll talk about the research that we do to try to understand questions like that. And just sort of to give you an idea, artists clearly know. And again, if you darken this, you'll be able to see. There's a gorgeous painting where the woman is wearing both velvet and silk, and they know how to capture the right visual features so that if you were to look at it, you too, super subtle on the velvet, but you can tell that's a velvet and silk combination. So that's one of the questions we'll answer during this talk. While you're looking at materials, and so there's a natural evolution, I added this part of the talk, you start thinking about style a lot. The materials that we work with and we live with play a big role, as I said, in the clothing we wear, so style is one part of that, but also in every product you interact with. And there's a lot of work that goes in industrial design and product design to get you beautiful items that you interact with that are both functional and useful and what you actually want to work with. So I'm going to talk about style in that context, and it all relates to this understanding of materials and objects in general. And so the talk's kind of structured like this. There's sort of three parts to the talk. I'll first talk about modeling and editing materials, and there we'll stay more at the sort of partly at the physics side and more at the just at the bits, changing the bits and trying to understand how you can change appearance. And I'll talk about both physical models and deep feature editing. Then we'll step up a little bit and look at higher level material understanding. Can we do material recognition, intrinsic image decomposition? And so again, that's work that's, and there's a body of work in that space. And then we step even higher level. Style is pretty misunderstood or not well understood. And how can we recognize style and what can we do in that context? And all of these, the work that I'll talk about today, fundamentally leverages the unprecedented amount of data that we have the luxury of having access to right now in this time, in this moment of time. So I'm very excited about what we can do, but more importantly, what we should be doing going forward too with all this great data. So the first part, as I said, we'll talk about modeling and editing materials, and I'll start off by talking about physical models. So I'd ask the question, what makes silk look like silk or velvet look like velvet? So here are two images of silk and velvet, and again, I think the moment you look at it, you'll instantly recognize that that is what they are. These are not photographs, these are rendered images that are produced using models in my group, and I'll talk briefly about how you can produce models of this fidelity that capture the right features. And silk, you can see, has that characteristic sheen and glow and shimmer to it, and the velvet has that characteristic asperity scattering on the rim of that particular object that's down there, and you can tell it's velvet based on that. So why do they look the way they look? What's different between them? The answer is the structure of the material. So what do I mean by that? We can look a little closer at the structure. What we did in our group is actually we took CT scans of these fabrics. So this is a CT scan of velvet. On the top left, you see the swatch of velvet we sent in for the CT scan. In the middle are the slices of velvet of the CT scans. And on the right is a 3D visualization. We're doing a sweep from the top to the bottom. So you start off at the tips of the velvet, and you go down to the substrate on which it is. And you can see first the tips come in, but there's a very clear structure on the right the visualization shows of the yarns and the fibers that are sticking out of the substrate for velvet. That contributes to the appearance of velvet. Conversely, how does silk look? Well, very, very different. Silk is very tightly woven warp and weft yarns that are together, and there's not that much depth to it at all. It's pretty tight to the surface, and that plays a big role in why it shines so nicely. So in my group, we've been developing these micron resolution from CT scans models. And the idea is that we're using it for industrial and textile design. So why do we need this level of detail and quality? Because if you're designing prototypes before you actually send them off to the mill or before you send them off to the loom, you want to visualize them, believe that you're getting what you actually wanted, and then send them off to save time and money and energy on all parts. So how do we go about doing this? As I said, we start off with CT scans of these materials, and that gives you the structure, but we all know that the appearance is defined by the optical properties too. So we have a second phase where we combine them with photographs. We initially started with very few photographs, but we've also done sort of more extensive, different lighting, different cameras, different viewpoints, experimentation to do appearance matching to come up with finally a complete fabric model that includes both the structure and the optics of its appearance. And I'll just give you a hint of it. And I should just go back. At the bottom, you see there's a project we started in 2010 in my group. So it's been going on for 8 years. So there's a large body of work. I'm trying to just give you an intuition for the high-level insights that we use and then what lessons we learn. Okay, so how do we get the model to represent these fabrics? We use, in our first iteration, we use what we call microflake models. The idea is you take your volume and you represent, each voxel represents some part of this model, where a yarn, for example, you can see yarns in that silk slice, and you can see an entire yarn is there. Each voxel contributes to some part of that yarn's appearance. And in fact, we characterize it with 4 parameters. And I'll quickly just show them to you. You can go and look at the paper in detail. But the idea is they give you some idea of the density of the volume, the orientation of the volume, and then the optical properties, which are the albedo, so the single scattering albedo, and some idea of the spread, which is kind of like the shininess or the gloss or the specularity, if you will. Very, very, I'm being very reductionist here. The paper has a complete model. But the key idea is then you can get the arrangement information from your CT scans, and you can get From the photographs, you can get the optical information, and once you combine these two, you then get models that are complete. So here, for example, on the left is a structure, and the right I'm showing you videos, and videos are very important, particularly to assess the quality. As you can see, the velvet has that right asperity scattering that's called from the perception community, and the bottom, the silk, has that gloss and the sheen that you expect. So that was, as I said, we've been working on it for a while. Since then, we've actually gone a step farther. We've developed procedural models rather than these very heavy volumetric models that actually capture the yarns, the plies that wind together to form yarns, the fibers that wind around to create the plies, etc. And all of these fiber level detail turns out to be very important to get really accurate appearance. And we have about 22 parameters that we fit to get these really rich models of yarns and fibers. And once you have this power, you can actually do amazing things. So for example, here are 2 different silk yarns that we've captured. On the left is a photograph, on the right for each one of them is the rendering with our model. It's reasonable, it's not fully accurate, but it's good enough. And on the left here is then what you can do when you're editing these yarns. Because you actually understand their properties, you can change them, you can unwind them, for example, and then produce, for example, a completely different kind of yarn. You can predict this appearance when you're, as a textile designer, trying to figure out if you want to do this, how's it going to change the macro appearance of this object, and then if you'd like it or not, accordingly you commit to making more of that particular textile. And overall, we are building essentially these pipelines to try to produce models that represent reality as best we can. So here is, there are 2 images. One of this is a photograph, and one is a rendered image of a yarn, of a fabric that we had actually acquired using all the techniques that I've talked about. And it's a little hard to see, but hopefully you believe that they're actually pretty close, and you can imagine that using them for textile design. The one on the left is the real one, the one on the right is the virtual one. Okay, so you may ask yourselves, particularly this is more on the graphic side of work, do we really need this level of detail to get realism and predictive appearance? And that was basically the question that I started asking. This is very useful for designers, but it'll be great. Human beings are able to understand silk versus cotton versus velvet at a much higher level. Can we leverage knowledge from human perception to drive better models? I don't have an answer to that yet. I'll talk about work we've done here, and I hope that future research will be to try to bring these 2 worlds together. At least that's my dream. So we started stepping back, and now I'm not going to talk about actually fabrics, but talk about different materials. Can you edit them without these incredibly detailed physical models? And I'll actually talk about a project which was at CVPR last year on face editing. And a particular example in that, though the problem that we looked at is more general, we looked at modifying faces to not only add facial hair, but also age a person, various other things like glasses, the usual stuff that you've been seeing in the context of GANs. This is not a GAN project, though. This was pre-using GANs for those kind of editing. But the question was a simple one: can we do this kind of very detailed material editing without the crazy models, right? So I want to add facial hair. There's a version of it where I do all the stuff where we model every yarn, etc., or every hair. And in fact, there are projects that do that in computer graphics. So this is what a professional artist could potentially produce after half an hour of effort and very complex models. And what we try to do is, using knowledge of the large amount of images that are out there, can we use some sort of deep feature stuff, and I'll tell you what that stuff is, to get intuitive results that capture the same effect. So this particular project was deep feature interpolation that can now, in 3 minutes, and it's all compute, no manual effort, produce these kinds of effects. What's interesting is it tells us a lot about how maybe these effects play a role visually and perceptually, and I'm more hoping that understanding can drive better models going forward. Okay, so how does deep feature interpolation work? So this gets back to that original point I was making, which is that we really have an unprecedented amount of data. You all know this. So we have lots of images of people with and without mustaches. I'm just using the particular example of facial hair. Now, the important thing to note is we don't have the same person. So this is Robert Downey Jr. is the person we want to add facial hair to. We have examples of him in lots of internet examples of him, but we don't necessarily have him with facial hair. So we have distributions that have no mustache, distributions that plus mustache. How do we make the transformation between them? The idea we had was interesting because it's actually surprisingly simple. It actually builds up something that Bengio had posited in 2013, which is that the idea that feature space is actually locally linear. So when you learn all your classifiers in deep learning, you essentially learn to separate out the positive and the negative examples. But the question was, can we use that local part of feature space to do edits and to change the appearance of objects because it's locally linear? How would we go about doing that? That was a question we asked. And as you can see on the left is color space. Color space is disorganized. In feature space, there is some hope because it's organized based on the desire to classify these things into positive and negative. So I'll just give you a quick summary of the algorithm, and then I'll show you some of the results. So the idea is you take these positive examples. So say you have Robert Downey Jr.'s face, and you have an attribute that you want to change on his face. He didn't have a mustache, he didn't have facial hair, and you want to add facial hair, right? So that's the attribute. What you do is you go and find the closest neighbors, the 100 closest neighbors with the attribute and without the attribute. Okay, so now these are completely unaligned images, and these are not images that are paired. They are not images of the same person. They are of completely different people, but they are on the internet and available to you. And what you do is you map all of those positive and negative set images into feature space, and I'll show you which part of how we actually map it. And then you also take Robert Downey Jr. and you map him to the same feature space. And the particular thing you have to do is we used VGG18, and the particular layers are the three that were shown, 3, 4, and 5 of those regions were what we picked. Why did we pick those? We actually did a lot of exploration. It turns out it's incredibly effective. VGG19 is magical, and this is like if there's no other message you take that one. And so those features really work beautifully in feature space for capturing the appearance. Okay, so now we've mapped all these points in feature space. How do I go from the positive example to the negative example? We tried a bunch of things, but one simple thing worked so well that we felt we had to write it up as a paper. You take the average in feature space of the positive and the negative, and you subtract them. And we call that an attribute vector. That's the attribute of add facial hair. With the right set of examples that you're using for the positive, negative, essentially you're removing all the differences and capturing the essence of what it means to add facial hair in this vector. The results basically suggest that that's what's happening, which is pretty powerful. And then when you start off with the position of Robert Downey Jr., the original input image, you go along that attribute vector. Remember, it's because we're doing linear interpolation in this locally linear space, in feature space. And then you get your output, which has hopefully the right effect. And so once you have that output position, which is a linear interpolant, you then reconstruct, and we use Mahendran and Vidaldi's regularization in there. And putting it all together, that's the high-level idea, just linear interpolation in feature space. Here are the results you get. As I said, it is surprisingly effective, and that's one of the reasons we actually wanted to put it out there. Before that, there was a lot of work, and in fact, the competing algorithm at that time was AE-GAN, which was working on much smaller images because of all the downsampling, et cetera, that you need to do and fitting in there. Here, there's no learning going on. We're taking these very, very large feature vectors. We just taken the third, fourth, and fifth, but then you interpolate there, and you can produce amazingly high quality results. Because there's no downsampling, et cetera, you can do it on high resolution images. So we run it at 1,000 by 1,000 images in 5 minutes, no problem. And the size, it scales linearly with size, so you can make it much faster on smaller images. But then here are other effects you can get. Here's the same input and the person looking younger versus older. Here's another example of somebody looking younger versus older. And using the same, you pick different attributes. In this age, you're picking age. Here's an example of somebody adding both age and a beard to them, and on the right, adding a beard to them. Since then, as I said, this was in CVPR last year, there's a lot of other work, Pix2Pix, CycleGAN, et cetera. They're all looking at this problem. What we've actually found is that DF5 is very stable. It's not even learning. It's just using the right feature space for its transformations. We're actually using it to produce training data for pix to pix, et cetera. So there's a bunch of work we're doing there, and it seems to be working really well. So what do I want? What's the take-home message? The take-home message is that this works so well is surprising and interesting and worthy of exploration. And that's one of the things that I would like to continue to do, and I hope other people will also just poke around, try to understand what's going on with these attribute vectors, what are they encoding, what can we do with that. Okay, so that's one, face editing. Style editing. Again, how did I get involved? Style editing often results in changing the material properties. It also changes many other things in images, but I got interested in it because when you're changing the style of an image, you're often changing lighting, material, etc. Why does it work so well? So what is style editing? Just to give you a quick, this paper was also at CVPR. Given an input image and a style image, you take the input image and you make it in the style S, okay? And it originally came, Gaddis did some really beautiful work. All of you saw this probably, and you played with it, or there's some app that you've uploaded your photograph on. So it's incredibly powerful that it works. And the key insight they had in their original paper was that you can split images into sort of the content. The content comes from the input image that you're trying to transform. The style comes from the style image. And you use the gram matrix in feature space to capture the style. You have the content from your input image. And if you have two losses, one to preserve content and one to preserve style, you can put them together and achieve really great results. So this is all, I'm just summarizing Gaddis's work. So Gaddis's work was there's two types of losses, content loss and style loss, defined in feature space, and the key idea is that the gram matrix captures the style globally for the image. You've seen these results from Gaddis, just absolutely gorgeous. The input image is on the top left, and the other three are stylized versions, each in the style shown in the inset there. So when we came to that, we were really excited about this because it's such a powerful technique. But the question was, what happens when you apply it to photos? So when you apply Gaddis's algorithm to photos, you can see that it has stylized the image, but it doesn't quite look like a photo anymore. You can see all the windows are warped because it's got more of a painterly guarantee, if you will, or a painterly idea of what the loss is. And we wanted to maintain the idea that it's a photorealistic photo, just convert the style. So that's what we did, and so this is the Gaddis output, and this is our output. And you can see this is in the style of the image on the right, but it's done, but it still looks like a photorealistic image. So how do we do that? I recommend reading the supplementary material of this paper because there are a lot of things we tried that didn't work that we put into the supplementary. And then I'll tell you what we did do that works, because it's very simple, but you need to appreciate it comes after like months and months of trying. So what we did actually, what we realized is that we can use the matting Laplacian. So Anat Levin introduced the matting Laplacian, which is sort of this locally affine color transform for a patch. And they used it in the context of matting. But you can add the matting Laplacian term, another loss term, into your style transfer algorithm, where essentially you're saying that you're maintaining photorealism in your optimization by constraining your transform to be locally affine in color space. So you're saying your output should preserve edges. That's the high-level intuition of what it's doing. Please read the paper for more details. But you're saying take your stylization, take your content, and preserve this locally affine transform. And if you do that, your loss term gets an extra term. This is a photorealistic loss term. And once you add that in, again, you get very powerful results. So on the input is here, I've shown zoom ins. There's a neural style, and ours is on the right, and you can see it really cleans up the image so that it looks still like a photograph and not very painterly. Here's another example. Our result on the right, neural style transfer. And they have different objectives. I just show them as a comparison to appreciate it. And you can appreciate it more in the zoom-ins. The neural style really feels like a stylized output, whereas on the right, it looks perhaps like a photograph, more like a photograph, but with the style of the input style image. Okay. So what I like most about these techniques, so I put them out there partly because they're very different. They're looking at stylization, they're looking at feature interpolation. But what's interesting is deep features seem to have a lot of power in them, and interpreting them and working with them would be the way it would be great. Also, particularly, I would like to actually link them up with the physical models and come up with solutions that capture the strengths of both. And that remains, I would say, a grand challenge. At least this is one of the things that my group is starting to work on, but I think it's a very exciting area. Okay, So that's sort of the first piece. I'm going to step back and now talk about material understanding. As I said, understanding materials, we've been talking about, changing them, but can you recognize them? So this is something that I've been very interested in. And when we first started on this project, again, I started in 2013. So partly I'm covering this here because I want to describe all the data that we've collected that I hope everybody will use and focus more on material understanding as we go forward. So when we first started this project, as I said, there's lots of great data of how materials are in interiors, and we got millions of images from Flickr, and we created data sets that I'll describe briefly that capture segmentations of materials, give us point clicks and named material points in data sets, and also pairwise ordinal relations. And I'll talk about each one of them and explain what they're useful for, and I hope that more people will use them. They've been getting a lot of visibility and use, but always good to get more converts. So we first introduced open surfaces in 2013, where the problem we were trying to do, as I said, when we started that's when deep learning was ramping up. There was ImageNet, but there was a Pascal, all of that data, but there was nothing really in the context of materials. There were small laboratory material data sets of like 100 to 110 data points, and there's some amount of data, but we wanted to really push it to sort of the internet scale, getting to that ImageNet kind of feel to it. So in open surfaces, and I'll just quickly show you what we did. We created, this is a large-scale Mechanical Turk project where we created interfaces and tools to first get material segmentation. So there we segment, the user is segmenting the floor. Then they're naming the material, they're calling it wood. Then they're rectifying the texture. And this we use a combination of vanishing points and user input because people are not very good, but vanishing points also has its problems. And then finally, this is the hardest task. We actually got from them specular and diffuse information to understand the material properties. So this is contrast and distinctiveness of gloss. Turns out that's a very hard task for people. So we collected some amount of data. So we collected about 110,000 segmentations of this level of detail. And it turns out that this task that we created ended up being very useful. So Microsoft Cocoa segmentation is based on the tool that we developed in the context of open surfaces. So if you've done or looked at those segmentations, you know how that came up. We have about 25,000 rectified textures and about 50,000 reflectances. And it's public, so please use it. As I said, it's a large crowdsourced data set. And there's different categories. It'll be great to actually expand the categories and go forward. So that was our first foray. But that wasn't enough data to actually get deep learning algorithms to actually work. So in our next project, which was in CVPR15, we did what is called materials in context, where we started off with the open surfaces data, but it was pretty expensive. So here's an example of an open surface segmentation. It's great. Somebody actually went in and segmented the dog out and took the nose out, saying the dog's fur is different from the nose. So they did exactly what we told them to do in our crowdsourcing task, and gave us a beautiful segmentation, but it costs about $0.33 to segment one of those segments. And what you need for deep learning is much, much more data. So we added basically weak supervision in the form of point clicks. So we got a lot of new annotations of material names, but no segmentations, no rectified textures, and no diffuse and gloss parameters. But this is a lot cheaper. It's $0.00 rather than $0.00. So we could collect 2 million of these segmentations and over 20 categories of data. So at that point, in the wild data sets, there were a lot of great material data sets, as I said, but in the wild, there was a Flickr material data set from MIT, which had about 10 categories, and we wanted to expand that out. When we published the paper, and so this always has a property, anytime you talk about deep learning, if you present it 6 months later, it's already become obsolete. So this is 2 years ago. At that particular CVPR, there were 3 papers on semantic segmentation. Before that, lots of people were doing classification, but the semantic segmentation, 2 were in object detection. We did ours in the context of materials, but they were all starting to bark up what is now, the mask RCNN and all of that stuff. This was the CVPR at which a lot of that original semantic segmentation papers came in. So we did a sliding CNN. As I said, this is old-fashioned now, but we did a sliding CNN then. We did a prediction map of the materials. And then that gets you about this far in terms of recognizing materials in a scene. It's okay. It's fine for certain tasks. It's not okay for editing or any of the deeper, the more refined kinds of algorithms that I've been talking about when we're editing things. So at that point, we had added also a dense CRF. This is Philip Cranbull had done this beautiful work on very fast dense CRFs. And we used that formulation along with the prediction maps so that you match the predictions in the unary term and you use the binary term to actually deal with proper clean segmentations, and we produced results like the one on the right. The main reason I show it, as I said, 2015 is ancient history in deep learning. The main reason I show it actually is to show you the results. When we published this, only best recognition was about 40% in 10 categories. This achieved about 85% in 20 categories, but the needle hasn't moved much since then, and human beings can do 95, 97%. So we need more attention to this area of material recognition, and that's one of the reasons I put it up there. There's still a gap between what we can do and what should be done, and hopefully more people will work on it. And here, by the way, is the final clean, labeled output that you can see. Here are some more results. This is a good start for materials, and why do we need all of these materials? It depends on the task, and actually in follow-up work, we've looked at this question of why do you need these labels? If you're doing material editing, you really do need these fine-grained labels. If you're doing something like robotic manipulation, you actually want to understand the material and you might want to understand its mechanical properties. So there's a lot of work now that there's interest ramping up, particularly in the context of robotic grasping and manipulation that goes beyond objects that I hope will now look more at materials going forward. Okay, and then the last data set, again, this is started a few, as we were collecting these point clicks, we were actually thinking about what are people good at giving data at and what are they bad at. And what we wanted to do is not just get the material labels, it would be nice if we could get some intrinsic image decomposition, essentially the shading and the lighting, and separate them out. That would give us much more power than just having the name. That was what we had hoped. So that started a whole bunch of work in intrinsic images in the wild, which I'll briefly talk about. Okay, so intrinsic images is a revered and gold problem that has been around forever. And the key idea you all know, you take an input image and you split it into reflectance and shading, and it's been around forever. It is ill-posed. Fundamentally, you're taking one input and splitting it into two. And so there's lots of great ideas that people have had on smoothing, assuming smooth shading, assume discontinuities represent reflectances, all of these various ideas that they have then put into the decomposition and tried to come up with various decompositions. It remains an unsolved and hard problem. And the reason is, a lot of the work that was happening actually in intrinsic images was happening in the context of using a relatively simple data set, which I'll talk about briefly. And so when you took those algorithms and applied them to real images like these, they didn't work. They often broke down. There was much more complex illumination, materials, geometry, the assumptions didn't work, etc. So when we started looking at this problem, our first thing was, well, before we even start trying to solve the problem, and we have a solution in the paper, I'll only talk about one piece. What's the data set we need to know if we are making any progress at all? So that was how we arrived at creating the data set that I'm going to present shortly. And the hope was to capture real-world complexity. So as I said, there was a great data set out of MIT. This is by Roger Gross, which has been used for a lot of intrinsic image decomposition. And what they did is they took their inputs, about 20 figurines in the lab, very carefully and meticulously measured. They sprayed them to get the shading, divided that from the original input image to produce the final reflectance, right? Well, that data set was used to drive a lot of the algorithm development, and that was wonderful, but people were getting really low errors on the data set, and then when you took it out in the real world, it didn't work, because that data set is not really representative of the real world. So we said, well, let's go and take real world images, let's take some real world images. Well, we can't apply the same idea of just spray painting it to get data, because that is, I mean, you could actually, we even thought about it, whether there's a lab setting in which we can get these kind of small scenes and do a better job. But the reality was there will always be toy small scenes that you can play with in a lab. And we wanted sort of the internet level of photographs that you want get rich complexity from. So we can't spray paint it. What can we do? Can we ask humans to give us annotations of reflectance? And we'd already done that in open surfaces. We'd asked people to give us diffuse albedo and gloss parameters. But we knew that they actually really struggled with that task. So instead what we did is we asked them something that they're actually good at. Human beings are pretty good at telling relative reflectance between two surfaces. So they can say this one is lighter, that surface is darker. So we created a new crowdsourced data set of reflectance comparisons. And what we did is we took 5,000 images in which we sparsely annotated pairs of comparisons, as shown on the left. And on the right, we got some denser. It's not really dense. I mean, dense would be for every pixel if you knew the relative pairwise things. But we have a denser annotation for the images on the right. And I'll explain sort of these cryptic pictures, the symbols on it shortly. But we got about 5 million judgments. And so what was the data we collected? As I said, the key insight was that human beings are good at relative reflectance. So we would give them 2 points and say which data has a darker surface color, and then combine that together in a judgment. Now in this case, just as an illustrative example, we have low confidence because they don't actually agree. They should actually agree in this case, it's a simple case, but the confidence is 0.1, and so we actually put that, when we label those 2 points, we show a bar showing an equal size to show that they have the same reflectance, but we have low confidence, that's why it's an orange. Meanwhile, if we took this, if we took this pair, then we know that the people seem to believe that 1 has a darker reflectance than 2, which is good, because that's true. And then we can give a judgment that 1 is the darker of the 2, and that we have a higher confidence in it. And so essentially, those are the judgments we collected. And so when I showed you that picture, I was showing you those judgments. So in a scene like this is the kind of judgments we would get. The main thing to note is if you look at all of the walls, we're able to actually, something happened, yeah. In all of these regions, you can see we are having these nice bars that connect the points that's saying that they're equal reflectance and that we are highly confident. That's why they're blue bars. And if you look at the dark cabinet on the left and the other areas around it, there are those less than sign, which is showing that the cabinet is darker than the rest of the world. So this is the data that's out there. Lots of people have been using it. Please use it if you're interested in this problem. But along the way, you also have to ask a more fundamental question when you have such data is, well, what is the metric you should be optimizing? This is the nature of all of deep learning. Everything comes down to the data you use and the metric you use. And if you ask the wrong question in the metric, and if you use biased data, you get bad results. That is like the core sort of thing that you need to be always vigilant about. So in this case, we came up with a new metric. We had realized that lots of intrinsic image algorithms are getting 0 or close to 0 error because they were optimizing on the MIT data set and a very simple metric, mean square error. And so we came up with something called the weighted human disagreement rate. Sorry, it's a terrible name, but WHTR is now being used in a bunch of algorithms. The idea is that you compare the crowdsourcing human judgments with whatever your algorithm produces. So if your algorithm produces a certain decomposed reflectance, you convert that into judgments, and then you feed them both and weight it appropriately by confidence in your human judgments. That gives you a measure that gives you a better sense of intrinsic image decomposition based on human judgments, whether it will be good from a human point of view, from a perceptual point of view. So in that paper, at that point, we had the best algorithm, but that's not the main point of this graph. Lots of people have done some beautiful work to follow up on it. The main thing is that the WHTR now, which is the measure of error, has dropped. When we did it was about 24%, has dropped to like 15, 16% in the best algorithms I know of right now. But humans are still at about 8%. So again, there's a gap between what people can perceive and what algorithms can do, and closing that gap remains something that's interesting. As I said, when you get in the data set business, you also have to be careful because you end up, people optimize to your data set and to your metric. And one thing we had done is we'd collected reflectance information because people are good at that. Well, it turns out that that lets your algorithm shuffle all your error into the shading. It does a great job on the reflectance, shuffles it into the shading, and there's not much you can do. Bad algorithms look like they're good. So in the follow-up paper at CVPR, we added shading annotations where we thought, okay, same idea. We didn't really think this would work, but same idea, can we get comparisons of lighter and darker shading? Turns out people are really, really bad at this. They can't do this at all. That is not something go and try it out, but that's not something you're good at. So we had to very carefully design the kind of data we get from people. I'll let you read it in the paper, but the idea is We collect the green and the cyan information, which is we tell people to give approximately constant shading. They can do that, so we get large regions of green. And in the cyan, when there's a nice sharp discontinuity in shading, we ask people to point that out, and then we can find it in the cyan points. The red points come from depth and normal discontinuities from RGB data, so they are not crowdsourced. But together, we believe that this, if you're in the business of intrinsic image decomposition, this data set, hopefully with the shading and the reflectances, will keep you honest, we hope, to get a better algorithm that works in the wild. Okay, so that's this part of the talk. So real quick, it's mainly, as I said, materials in the wild are often ignored. It's a problem that actually needs more attention, needs better data, needs better metrics, and needs better algorithms. So again, I hope we've been working some on this space. I hope more people will get excited about working in that. And now I'll get back to the last piece of the talk, which is stepping even farther out, away from recognition. You're going further up the pipeline to style, which is very, very poorly understood. The definition of style itself remains wide open. But lots of great work is happening in this area, and I'd love to see more of it. So I'm going to talk a bit about two of the projects here. One, as Kristen mentioned, was the core of our company, GrockStyle, and I'll talk a bit about what it does. So it does product recognition. So how did we arrive here? We published this paper at WACV18. It uses techniques from this community, and actually we just had a launch yesterday, so if I was a little distracted yesterday, I'll describe what we did. So when we first came to this, I don't know how many of you have played with house or ever thought of remodeling your home, but there are sites that have tons and tons of inspirational imagery for home design, and people spend a lot of time when they're redesigning their home on these sites. So how much data do they have? A lot, like millions of images, and you get lost in those sites for hours, and then you come out, and it's a little hard to figure out what should you do. Now, how do you actually translate that to your home? So the kinds of questions that we found on sites like this are, firstly, the what is it question. So people see something they really like, but they don't know what it is. What is this countertop? What is this particular, pendant lighting? What is the subway tile you used in this kitchen? Those are some examples. And then once they see something they like, they have the where is it used question, and this is related to people not feeling very confident in their style decisions. There are some people who believe they have great style and great design, but most of us, me included, don't really feel like I am confident to make very bold style choices. I would really love a designer to help me with that because they are trained at that. And so the kinds of questions that come up here, people say, well, I know what that is maybe, but I don't know what to use it with. Can you give me suggestions? And people might say, here are some chairs that go with it, and look, here's a photograph that shows that. And you say, oh, that looks cool, I'll get it, right? So that was the domain that we were very interested in looking at. And the broad problem is product recognition. And so I'll just summarize what the two problems are. You walk into your friend's backyard, you see something like this, looks weird, not really sure what it is. So first question is, what is it? And you don't really, it's not at an coarse object recognition where somebody says actually it's a fire pit, it turns out. That's not enough. You want to go to the fine-grained recognition of knowing not only is it a fire pit, that's the category, but it's this particular fire pit sold by this person. The sold by part is the e-commerce side, but the exact detail of the fine-grained recognition is what you want. That's the computer vision side. And once I recognize it, as I said, on the inspiration side, it'll be great to see how people use it as a fire pit, as a torch, etc., because that gives people more confidence when they're trying to design their homes. So we published a paper. I'll talk about the technique we did there, and then we spun out a company which still is a 10-person startup in San Francisco, and we just had a launch, and I'll talk about that. So the problem, from the computer vision point of view, what was the problem? We have messy, in the wild, in-context data that comes from photographs that people upload on social media or they have on their websites, the retailers have on their websites. And we have very clean manufacturer product images that are iconic images that represent those products. And our goal is to try to find the relationship between these two. And how do you do that? At that time, as I said, we started this project in 2014. Pretty, well-known stuff for modern times, trained a Siamese network to learn a joint embedding, okay? And so the architecture looks something like this. Since we first published the paper, we've of course improved it a lot, but here's the high-level idea. You have a Siamese network, you have the messy images on the top coming in and the clean images at the bottom, and you essentially have a mirror copy of the two, and you have contrastive loss. You pull together the things that are similar, you push apart the things that are dissimilar, and that's the loss that you train for. Now you learn an embedding, and then the problem becomes your iconic images project to the same place as your messy images. That would be the ideal solution. And then different objects project to different parts of the embedding. That again would be the ideal thing. And then when you want to solve your what is it problem, you project in and you go and you look up exactly what it is. When you want to solve your where is it problem, you go and look up all the images that used it, and now you've got this bidirectional way of seeing, exploring inspirational images and finding products as you need them. So I'll pick up the pace a bit. This is some idea of the embedding we got. The main thing to note, if you look at the top right, there's the sort of the spindly-legged office chairs. So there's some coherence to this. This is the T-SNE visualization. And here, those are the various different pieces. I'm just going to show you the results, and then I'll show you a demo, not a live demo, a recorded demo of it that got launched. So these are the kinds of queries we could answer. Here's the product you want to find. This is a challenging case because the product is basically made of plastic, so you can see a lot of the background, but you still want to figure out what it is. And those are the top 3 results we provide. So you can see it does a good job of finding exactly the right match, which is the third result in this list. Here's a highly occluded object. If you try to find it, that's the canonical object. Here are the results that we get with our technique. And then here, this is to me the crucial part for why visual search is exciting, why we did this company in the first place. Text search has completely changed how we do business. Nobody ever calls up a store or does anything like that to find out information. You look up everything online by typing words right now or giving it a verbal command. Visual search is right on the threshold of being where we will be going forward. So you take a picture of something, you just want to know what it is, you're not going to try to use words to describe it. Here's a perfect example. It's very hard to figure out what words you would use to describe this particular chandelier, and this is a perfect example where visual search works. Same with those chandeliers up there, by the way. I tried them when I came in this morning. And so the idea is, if you enter something like that and say, what is it? We can just return the answer because you don't need to find the words to describe what that crazy looking thing is. It turns out that this kind of an embedding is actually very powerful. It actually figures out what is visually important to represent that particular object. So on the left is a query image, and here are different things that come up across different categories. So different objects, but same visual style is represented in all of them. And so you can use this to actually find things that pair up and match up, etc., which is part of also what people want to do. And here are more examples of that. You can see when you look at a certain wooden chair, it finds other things that have that same style. On the bottom, there's sort of this more eclectic pink, super bright style. Again, it finds different categories, but same visual style. I'll sort of go quickly. In our original paper, we had, performance results, which I'll point you to, but I'll mainly show you a demo. We had a launch yesterday at noon, actually, with the IKEA augmented reality app. And here are demos that are showing visual search with augmented reality. So this is using GrockStyle's technology and IKEA's augmented reality, and the idea is that now you can redesign the interiors, because if you look for some product, on the left, one of you is showing how a person is using it. On the right, you're redesigning some common area. And sorry, I just put those two together so that you can see them. We find the product in both cases. And then on the left, we stop. But on the right, we actually position it there. And now we can visualize how it looks in context because we wanted to add an extra couch into this room that only had one couch. It's a large common area. Here's how we could put it in. And now we can add more stuff in. Going forward, we are actually adding, visually similar and, recommendations to add more variety to this. All right. And the last piece is another aspect of style, which is now stepping up and looking at fashion. And actually, fashion not as shown by supermodels, which is amazing, but very different. We call this project Street Style because we wanted to actually capture what people are wearing in the world. How do they live in their lives? And again, this is all motivated by the fact that we do have access to unprecedented amount of real data of people living their lives across the world at all times of the day and night. Can we leverage that information to understand how people live, dress, etc.? So the broader project here, and I'll briefly talk about some results. So the idea with Street Style is we wanted to understand everyday users. We wanted to deal with a large scale, tens of millions of photos across the world and across several years. And the idea was to drive better analytics and better visual discovery. Can we find things that we can't find just if you don't have this visual data? Can we leverage that to gain insight in how people live and dress across the world? So we got Instagram data from 2013 to 2016. We then did face detection. We wanted to find the people in it and find the clothes they wear. So we just used simple stuff. We used Face++ for the face detection. We used DPM then, but since then we've upgraded that to more recent models. And we built what are called canonical crops from these Instagram pictures, where we got, I think, 8 million photos. So this shows some of them. And then we annotated a very small subset, 27,000 photos, with some set of attributes that we wanted to study. And so the attributes we looked at were things like, are you wearing glasses? Is the person wearing glasses, wearing a hat? Is there a collar present? What is the sleeve length, short sleeve, long sleeve, V-neck, U-neck? Are they wearing multiple layers? Are they wearing stripes, etc.? Wearing a jacket. Those are the set of attributes. And then just like in the previous work that I did for GrockStyle, we then designed, we got a CNN that, we came up with an embedding to classify all of these attributes in the large scale data set. That's how the embedding looks. This is a t-SNE visualization. That's the supervised part. What becomes interesting then is the next step that you can take in the unsupervised way to discover how people dress in this embedding. So for example, we then we got 400 GMMs, we fit 400 clusters to this data, and we looked at each of those clusters to see what it revealed about how people are dressing. And what it did is, the plaids we had already were part of our attributes, had discovered them, but what was interesting, unsupervised, it discovered things that we had not trained for. So it figured out that here was a cluster that showed people wearing jackets and having layers. And in fact, we got all kinds of clusters that gave us more insight into how people dress. So for example, there are people with jackets, but also with striped shirts, for example. So the fact that people combined those two was something that got revealed from the data, though we didn't actually feed it into our data. We didn't know that that's what people did. It told us how people dress across the world. Here's another example of, and actually there are a bunch of these, clusters real quick that you'll see when people wear dark glasses, they're also wearing dark glasses with jackets in cold places and black sweaters with white collars, etc. So it gives you a combination of information which you didn't have in your input that get revealed by looking at the embedding. So here's an example. Many people will wear gray. So the average image is shown on the right. You can see they're wearing some gray thing, but it's often a gray thing with a printed, this is sort of a common fashion theme that people use. I'm sure some of you are wearing gray hoodies with prints on it. Actually, nobody here. Interesting. So somehow, no, I see one. I see a gray hoodie with a print on it. But once you have these clusters, so on the left are the clusters, on the middle are the average images, you can also look how they arise in different parts of the world and across different times. So these are 4 clusters that we picked that happen to be very localized in space and time. And the top one is very actually traditional headgear in Lagos. The middle 2 are basically exposing that people wear the hijab in Cairo and Jakarta. So I'll go back and show you. So these are certain cities on which light up for those particular clusters. And you can see specific cities light up with specific clusters. And then on the y-axis, you actually see time. And that's another interesting thing. When you look at this bottom right graph, you can see that something's happening in certain times of the year. Then you look at the cluster on the left, and it's very obvious. It got cold, and so people are wearing dark jackets and hats. So it's very interesting to look at these clusters because they reveal part of human behavior that once you see it, you're like, oh yeah, that makes sense. But occasionally they reveal things that you actually didn't anticipate. And just so you know, these are the highly localized clusters. There are clusters that are not localized. So for those of you who wore a blue shirt, people wear blue shirts for professional settings all over the world. So not localized in space or time. These are standard way. Plaids are very common across the world. Black shirts people wear across the world at different times of the year. So it's interesting to see what are very specific to certain times and locations and what are not and are completely generic. One thing we also found, and I'll actually skip past, is we found strong correlation, temporal trends. So for example, New York City and Buenos Aires are opposite because northern and southern hemisphere. And in fact, when you look at the graph, you can see southern cities behave in the same way, northern cities behave in similar to each other and completely different from each other, anti-correlated with each other. And then one cluster that is just fun to show, this popped up, we didn't know what it was, there was a very, very high activation, and we were like, I wonder what this is. It was just very bright on the graph. So then we looked at it, and we got a graph like this that showed a very particular spike at a certain time of the year, in a certain year. Any guesses? It's a World Cup, so you get your printed yellow shirts of various kinds. And actually, it's interesting, it was there where around the same area where the World Cup was, but you can also see where different parts of the world where it's super popular, so people start wearing it at the same time, even though it's not the location of the World Cup. This data is out there. Please go to streetstyle.cs if you're interested in this stuff and play with it. All right, so to summarize, that's the style part. We just scratched the surface on trying to understand how people dress across the world. There's lots of interesting work in modeling trends, separating noise from signal, fine-grained recognition, et cetera, that we're actually ramping up on, but I think there's lots of exciting projects there. So what are the take-home messages of the talk? I am very excited about the unprecedented amount of data we have, and we should go beyond object detection to all the different ways in which you can use all this data. So particularly material appearance, very important, but often ignored. Not really. I mean, there are, of course, very exciting little subgroups of people who work on material appearance, but it needs even more, I think, engagement. Physics is important, and actually combining physics with deep learning, to me, is the holy grail. I think having one or the other is not really, in fact, reasonable. You need them both for the level of quality and understanding that we need to really build off those models. And so interpretability, et cetera, all comes into play. And style is really wide open and not very well understood, so I hope that that'll get more interest and excitement. And these are all the people who really do the work, and these are all the links if you're interested in them. And with that, I'm happy to take questions. Yeah.
I didn't want to go first, but this is a wonderful talk. I have a couple of questions. One is, when you talked about humans being able to tell brightness differences, there are times where human perception can be tricked, right?
Yes.
The Ted Adelson
Yes.
checkerboard
Yes.
type of thing.
So
you see that?
Right. So not brightness differences. That's the shading, that's the difficulty. The reflectance differences is what they can tell. And that was actually a critical part of our design when we first did it. And that's a very good. In fact, we used Ted Adelson's illusion. So people are good at saying bright material versus dark material to a certain extent, by the way. So we also have to give them some context. We have to give them not, very two completely separated regions. So that's actually was part of the design. We actually looked at nearby points where they had some context, but we're looking at separation only of reflectance there, which they could do.
Yeah.
Not the brightness, and in fact we would use the Adelson illusion to educate them. It's in our tutorial. But then when we went to the shading, that's when it started banging our head on the same questions again, and what we found is they could do this constant regions, and we would let them pick pairs of different shading. So that's where we didn't tell them which 2 points, we let them pick 2 points across a shadow boundary that they were comfortable with. So then they only picked high confidence points.
Okay.
But yeah, there's a lot of getting that right, which is a lot of subtlety to that.
So my second question is, what happened when you tested your software on the chandelier?
It worked. We found
Where do we buy it?
Not this slide, because this is kind of crazy, but we found a very cool, nice chandelier that you can potentially buy that's affordable, unlike this one, I imagine.
Anyone else?
You scared me.
So thank you for your talk. It was super interesting. So I have a question. I'm sure you know it, but there is a bunch of papers recent that try to estimate BRDF parameters from a single image.
Yeah.
But in the end, when you look at the results and you try to compare what is a good result, there is no clear metric to estimate BRDF. So I wonder, what is your opinion about this? If we either have to do very exhaustive human adjustments, or is there any other big data way to?
So this is a great question. Metrics are unsexy, but so important to our existence, and people don't spend enough effort worrying about them. So one of the things we actually have been realizing, this came up in the context of intrinsic image decomposition. It actually, and this is, everybody hates the answer, but I'll just say this is actually the right venue to say it. It depends on the application. The metric and the algorithm you use, I think, will be defined by the application. So if you want to change the material properties because you're doing special effects and you want to edit materials for that, that's a very different domain than if you want to estimate the lighting because you want to use those lighting estimates for, doing your depth reconstruction or something like that. And so this is not an answer people like to hear, but application-dependent metrics and evaluation, I think, is unfortunately the way to go. And as I said, this might be a less hostile audience to that concept that the application matters, and you actually have to get that right.
Yeah, I just wanted to ask you, going back to your intrinsic image decomposition work, right? Obviously, the model will break down if there are many peculiarities on the surface. And you mentioned that humans themselves don't agree on what the reflectance is, right? So could the deviation be explained by the presence of peculiarities on the surface?
Not in that case, because in the design of that data set, we remove glossy materials, we remove specular materials, we only pick it where there's high confidence for that data set. We should get the data for glossy materials, and actually for the shading annotations also, we remove the glossy materials, etc. So it is in the regime it should work in, and there is still a gap. And then there's a regime where it doesn't work in, where we really need answers for. So that's why it's an open question still, and lots of great stuff that I hope people will continue to do. Great. All right. Thank you.